Hearken, noble audience, and lend thine ears to a story of forms, one curved, one straight. Two lines, both alike in dignity, on the geometric plane where we lay our scene. Behold the steadfast Juliet, a ruler most unerring, simple, constant, with no twist in her tale. But the ever-changing slope of Romeo, a curve of boundless mystery, whose perfect roundness doth confound the eye that seeks to measure straightforwardly. Yet mark this wonder, when thou draweth nigh to Romeo's most intimate arc, he mirrors fair Juliet's gentle slope. From this sweet union springs forth a truth eternal, a distance derived, a secret unveiled, a story woven of lines and love.
The story of lines and curves has echoed through the ages, told and retold by geometers and visionaries. But it was Newton and Leibniz who gave it new dimensions, using straight lines to measure the ever-changing slopes of curves. Meanwhile, in the year 1656, another tale was unfolding, crafted by John Wallis, the architect of an infinite code. His masterpiece wove together the positive integers in perfect harmony. Even numbers appear twice in the numerator, paired with themselves to contribute to the balance. Odd numbers, too, are counted twice in the denominator, reflecting their symmetrical role. This dance of pairs creates a symphony of multiplication and division. And like the integers themselves, Wallis's code stretches on forever. Yet, a challenge emerges for our star-crossed lovers. By tradition, Romeo can only traverse curved paths, following the arcs of a circle. Juliet, steadfast in her ways, is bound to straight lines, traversing chords that link points across the circle. Their differing paths adds tension to their journey, but also reveals the beauty of a circle. The question we ask today: could Wallis's infinite code be more than a mathematical marvel? Might it hold the key for Romeo to find Juliet and unlock their eternal love?
But soft, how shall Romeo bridge the divide and encounter his beloved on sundered paths? Two allies assist his mathematical quest toward Wallis's key, and at best, Juliet.
Since Juliet's path is straight, Romeo begins his journey on a ruler, a simple 12-inch line. At the midpoint, 6 inches, stands the friar.
Travel to every integer point on the ruler, both left and right, and measure your distance from me.
The nurse, positioned at 6.5 inches, gives the same task, but with a twist.
Exclude the midpoint, 6.
To simplify, Romeo multiplies both numerator and denominator by 2, transforming values like 1 divided by 0.5 into 2 over 1. When Romeo multiplies the ratios of these adjusted distances, he discovers a pattern of integers. But Juliet is nowhere to be found.
Julie's path is straight, but she doesn't live on a ruler. She resides on a circle.
A line that's straight, with points along its span, now bent and curled to form a circle's plan. As Romeo seeks Juliet, he encounters what he knows, the distance curved. He measures arcs, while nurse and friar, the points they mark.
With renewed energy, Romeo reshapes the ruler into something new, something closer to Juliet's world, a circle. He flips and rotates the points from 12 to 0. The product formula on the left now represents distances from 6 to 12. The formula on the right represents distances from 6 to 0. As the ruler bends, Romeo notices something striking. A ruler, twisted into a circle, resembles a clock face. The midpoint, originally 6 inches, now aligns with 6 o'clock, and the other points naturally fall into place like numbers on a clock. To fully appreciate this transformation, Romeo reviews the arc from 6 to 5 to confirm this distance is indeed 1 inch. And then, through the symmetry of the circle, he is confident the distance between each number remains 1 inch. And once the right side is complete, Romeo mirrors the process for the left side, confirming the distance around the semicircle is 6 inches. And Romeo notices that while there are still 12 points, the two endpoints of the ruler, 0 and 12, now occupy the same location on the circle. These endpoints have merged into one, indicating a change in landscape from the ruler. Even though the endpoints have united, Romeo knows his journey to Juliet is far from complete. With the ruler fully reshaped, Romeo places the friar and nurse back in their positions, the friar at 6 and the nurse slightly offset at 6.5. And then he is struck by a profound idea. The distances have not changed, only the shape of their world. If the distances haven't changed, then the proportions haven't changed, and Romeo's answer remains the same. But he marvels at how a simple multiplication problem has transformed into something visually fresh on a circle. Inspired, Romeo doubles the number of points on the circle. The friar remains fixed at 6, while the nurse slightly shifts to 6.25, halfway between 6 and the next clockwise point. Romeo recalculates the friar to nurse product ratio and finds it slightly larger than before. Each step brings greater precision, and with every calculation, Romeo inches closer to Juliet.
If e'er these star-crossed lovers are to meet, reality in truth is imprecise. But joy, geometrists of old prepared a tool to which Romeo in hope applies his plight.
Next, Romeo takes a strategic step. He leaves behind arbitrary measurements and enters the realm of pure mathematical beauty, the unit circle. Here, the circumference is not 12 inches, but standardized to 2 times pi. With a radius of 1, every point on the circle embodies perfect mathematical proportions. Yet Romeo, still tethered to the physical world, envisions the radius of the unit circle as 1 inch, a familiar anchor in his increasingly abstract journey. With increased confidence in his elegant setup, Romeo divides the unit circle into 288 evenly spaced points, tiny markers arranged with flawless precision around its edge. The friar remains fixed at 6 o'clock, while the nurse shifts halfway between the friar and the next marker, a subtle offset Romeo must account for in his journey. But the key insight Romeo carries from the ruler is that it's not the physical distance between points that matters, but the even proportions between the points. On the unit circle, Romeo applies his method as before. For example, the friar to nurse ratio at 9 o'clock is 144 over 143, while at 3 o'clock it is 144 divided by 145. To calculate the final product, Romeo pairs points symmetrically around the circle. 2 over 1 times 2 over 3 times 4 over 3 times 4 over 5, and so on. This pairing captures the circle's natural symmetry and mirrors the structure of the Wallis product. By following this term-by-term approach, Romeo's method hums to the harmony of the circle, and the result increases slightly from before. And as he progresses, he senses a presence. Someone approaching the circle with a different method, but the same goal. Juliet is near.
The arc between 2 points upon the curve marks Romeo's path, from which he dare not swerve. Yet chords, those straight lines linking them with grace, are traced by crossing through the circle's space. In this true bridge, fair Juliet seeks solace, and so may find a different road to Wallis.
To crack the Wallis code, Juliet also compares the two distances for each point on the circle: the friar to point distance and the nurse to point distance. While Romeo follows the curved paths of the circle, using precise arc distances, Juliet chooses a different approach: the chord method. Her method measures straight line distances, connecting each point directly to the friar and the nurse. Her calculations, though tedious, rely on f, the fraction of the circle's circumference, ensuring consistency in her results clockwise and counterclockwise. But the nurse's slight offset introduces a small asymmetry into her measurements. Consider the distance from the friar to the point at 5 o'clock. Since the friar resides exactly at 6 o'clock, this distance is precisely 1/12 of the circle. However, the nurse, positioned slightly to the left of 6 o'clock, measures a slightly greater fraction for the same point. Likewise, the distance from the friar to 7 o'clock is also 1/12 of the circle, but for the nurse, shifted slightly from the friar, this fraction is slightly smaller than 1/12. This subtle asymmetry exists at every point and is the key to understanding the difference in their calculations. Despite using a straight line approach, Juliet's final result is remarkably close to Romeo's. This small but significant difference sparks an idea. Could there be a way to simplify the process? Perhaps a shortcut, a formula that captures the entire product in one elegant step. Juliet considers a new approach. What if she calculated all friar products first, then all nurse products, and only divided at the end? Inspired, Juliet refines her approach. Rather than calculating term by term, she separates the friar and nurse product entirely, seeking a cleaner method. She begins with the friar's distances, multiplying one by one. Despite the complexity, the final product resolves into a single striking integer, 288. Next, she calculates the nurse's slightly offset distances. Though the denominator lacks the tidy appearance of an integer, the final friar-to-nurse ratio remains unchanged, perfectly preserving her original result. This new process, however, feels far more elegant and efficient. But Juliet does not stop there. She recalls two secrets, whispered through time by the geometers of old, truths long preserved, waiting to be unveiled. The first secret reveals the friar's product is no accident. It is bound to the circle's very structure, reflecting the perfect balance of its 288 evenly proportioned points. The secret states, if we measure the distances from the friar to all the equally spaced points on the circle and multiply them together, the result is always the total number of points, in this case 288. However, since the friar himself occupies one of these points, Juliet omits the friar's own distance, leaving only 287 distances to compute. The second secret unveils something equally remarkable. If Juliet instead measures the distance from the nurse to all 288 points, including the friar, then multiplies them together, the result is always 2, no matter how many points are on the circle. Yet, one subtle asymmetry remains. Since Juliet ultimately wants a product over 287 points to match the friar's calculation, she must exclude the distance from the nurse to the friar. This final adjustment corrects the imbalance and preserves symmetry. To get a better glimpse of Juliet's crucial adjustment, let's zoom in to witness the details. Because there are 288 equally spaced points, f between any two adjacent points is 1 over 288, and since the nurse is halfway between point 144 and the next point, then the fraction of the circle from the nurse to the friar is 1/2 of 288. So the chord distance is 2 times the sine of pi times 0.5 divided by 288. With that key adjustment, her final product not only matches her previous calculations, but also aligns closely with Romeo's arcs. The symmetry of the circle has simplified what once seemed infinitely complex. As Juliet marvels at the harmony between their methods, a question lingers. What if the circle were divided into infinitely many points? Could this reveal even deeper truths?
In arcs and chords, our circle multiplies. As distance and proportion, its symmetry retains. As Romeo and Juliet approach the boundless line, infinity whispers of truths divine. What wonder awaits in this final embrace, where math and love unite in timeless grace.
As the points multiply, Romeo and Juliet watch their methods converge, like two paths destined to unite. Together, they ponder a single question. How do arcs and chords behave as the circle becomes infinitely detailed? At 288 points, some ratios seem distant from the friar's position, their alignment still incomplete. But as the points increase to 4,800, these ratios begin to draw nearer, inching toward harmony, as if drawn by an invisible force. At 24,000 points, again, distances shrink and ratios align. It's as though the ruler is a magnet, pulling the points toward balance. At 60,000 points, the original ratios are now so near to the friar that arcs and chords converge. What once were curved segments are now as precise as measurements on a ruler. And here lies their answer. At the edge of infinity, arcs and chords become one. What was once a difference in method vanishes. The path of a curve, the path of a line, now they are the same. Their calculations, though born from different worlds, now yield the same result. Juliet's shortcut, once merely an approximation, now stands as a path to truth. And with this realization, a new question arises. Can the process be simplified even further? Juliet's method, though elegant, required a final adjustment, a sign calculation that felt out of place. Could there be one last refinement, one final key to unlock the Wallis code? As the points draw even closer to the friar, so too does the nurse's position. She stands between the friar and the first point, a near imperceptible gap. Juliet's adjustment used the chord distance between the nurse and friar. But now, as n approaches infinity, the difference between chords and arcs vanishes. What once was an approximation now mirrors the truth. Romeo reconsiders Juliet's method. If the arc and chord are now alike, why not embrace the arc directly? With this single insight, they abandon the chord, choosing the circle's natural path. A calculation far simpler, yet sneakily accurate. This delta change reshapes their formula. The number of points disappears, replaced by something greater, the transcendental pi. With this shift, the Wallis code's final secret is revealed. Their journey converges to pi over 2. A constant, eternal, unshaken, tied to the essence of mathematics. And here a paradox emerges. Geometers of old used straight lines to approximate curves. Yet now, at the edge of infinity, it is the curve that reveals the straight. Not an approximation, not an estimate, a perfect truth. Once again, math delivers a surprising ending. Romeo and Juliet marvel at the stars, countless as the number in Wallis's code, yet not scattered in chaos, but arranged in silent harmony. Each star, a point in an infinite expanse. Each number, a step in an unbroken sequence. Stars above, numbers below, both stretching on forever, both bound by unseen, unwavering laws. Is it possible that the same unseen harmony guides both numbers and the stars? For a fleeting moment, they are no longer counting. They are beholding an eternal truth, etched into the fabric of the infinite.
What's in a name? That which we call Wallis code, by any other name, still constant remains. Yet uneasy grows the heart at rest, and to our lovers Basel shall prove a test. Though all is within a circle contained, a number line sees family estranged. And so good night until tomorrow, parting and math is such sweet sorrow. For never did a story more insight beget than this of Romeo and his Juliet.
Let's walk through some quick examples to follow the math of the code and to appreciate its beauty. We'll start with only 2 points. Let's view the setup using a straight line on the left and a circle on the right. Place the friar at the halfway point 1. Place the nurse halfway between 1 and 2. For Romeo's arc method, we travel to point 2, which is clockwise on the circle. This produces the fraction 2 over 1. Then travel to point 0, which is counterclockwise on the circle, and that produces the fraction 2/3. This gives us our familiar product, which is 4/3. And interesting enough, 2 over 1 represents a perfect octave in music, while 4/3 is a perfect third, giving Romeo's method a naturally harmonic start. Now let's expand to 4 points by adding points located at 3 and 9 o'clock on the circle and shifting the nurse to the halfway point between the friar and the next point. This introduces 2 more familiar terms, 4/3 times 4/5, which improves our estimate. Now a key concept is the endpoints 0 and 4. They are 2 separate points on a line, but on a circle, the endpoints merge into only 1 point. And notice the beauty is that we preserve symmetry by traveling to this point both clockwise and counterclockwise on the circle. Now let's analyze the 4-point circle using Juliet's method. To get better insight, we will use it using both basic geometry on the left and the sine formula on the right. Okay, from the friar to point 4. This is just the diameter of the circle, which is 2 times the radius, which equals 2. The chord length using our sine formula is 2 times sine of f times pi, where f is the fraction of the circle. F is 1/2 to the point 4. Sine of 1/2 pi is 1, so then multiply it by 2, and we reproduce the chord length 2. From the friar to point 3, this forms a right triangle with legs 1, so by the Pythagorean theorem, the hypotenuse is square root 2. And by symmetry, the friar to 1 point, that distance is also square root of 2. And using our formula, from friar to points 1 and 3, f equals 1/4. Recall the sine of pi over 4 equals the square root of 2 divided by 2, so the chord length is the square root of 2. And in high school, you may have memorized the formula for sine of pi over 4, but now you see it in action. Finish by multiplying the 3 distances to produce the result 4, which matches the secret 1 shortcut for n equals 4 points. At first, the nurse's product seems complicated, but with symmetry as our guide, it naturally comes together. With 4 points, we divide the circle into 4 equal parts, but from the friar's perspective. However, the nurse is halfway between the friar and the next point. So each of the 4 parts splits into 2, like Romeo and Juliet splitting a piece of pie in half. This gives us 8 equal parts around the circle. Now let's count the parts from the nurse to each point. To points 2 and 3, 1 part. To points 1 and 4, 3 parts. Okay, now that we have the fractions, let's substitute into our chord formula. This messy equation produces 2 copies of 3/8 and 2 copies of 1/8. And after all the calculations, the result lands on 2. Wait, 2. That's the result of the second secret. But we must adjust that result. Do you recall the adjustment? We originally included the chord between the nurse and the friar. So to remove that extra distance, divide by the nurse to friar chord distance. And we do this on both sides of the equation. But rather than thinking about it as an equation, think about it as a choice. Which side would you prefer to calculate? 3 chords or 1 chord using secret 2? Now, this choice is somewhat close for n equals 4. What would you choose if we solved for, say, for n equals 24? 23 chords or 1? Either way, for n equals 4, the result is 2.613. And this gives us the nurse's chord ratio, which becomes our denominator. Our final answer is the ratio of the friar's chord distance, or 4, and the nurse's chord distance to produce 1.531. If n equals 4 or n equals 24 is not enough, here's an animation for n equals 288. First, our friar distance. Then the nurse's distance. And I'm including the distance from the nurse to the friar to reveal our secret 2. Thanks for making it to the end. And if you found that Wallis left you intrigued, well, the story continues in part 2 with the Basel problem. Stay tuned.